Okay, so we're here to solve the question about direct method catch. In here, in the given informations, we got main memory here, which have one word per cell, 32-bit address, 8 GB total size of main memory. In our cache, we got 512 KB total size of cache and 64 bytes per line of cache. And the given address in hexadecimal is 0000E602. So our question here is A, what is the address in base 10? B, what line of cache is the cell in? C, which word is it in the cache line? D, which block is it in the main memory? E, what is the base 10 tag? And last question is what other cells are also in the same block with the given address. So before we answer this question, we have to convert every given number here into base 2 in order to be easy to divide and multiply it. So step 1, we got 32-bit address here in memory, which means we got 2 to the 32 words in memory, and we have 8 GB total size of memory here, which means 2 to the 3 times 2 to the 30, which will equal to 2 to the power of 32 bytes of total memory, main memory. And our cache, we got 512 KB total size of cache, which means 2 to the 9, 10, 2 to the 10, which equal to 2 to the power of 19 bytes of total cache. And we got 64 bytes per line of cache, which means 2 to the power of 6 byte per line of cache. So this is our important recipe to answer other questions.
Now we want to know the size in bits in the address of the tag, line, and word. So for step 2, we want to know the size of the word per line. So to know that, we use the given information of the total size of the memory, that is 2 to 33, divided by the numbers of words in the main memory, that is 2 to 32. So now we have the number of bytes in a word, and then we take the number of bytes in a line that is given, and we divide by the number of bytes in a word. With that, we know that it's 2 to the 5 words per line. Using the log, we discover the size in bits of one word is 5 bits. And now we can put here.
There's a number of different ways to solve this, but for this example, we're gonna solve the size of the line next. So for step 3, to solve the size of the line, we need to grab the size of the cache, which is 2 to the power of 19, and the number of bytes per line, which is 2 to the power of 6. And so 2 to the power of 19 divided by 2 to the power of 6, we get 2 to the power of 13 lines per cache, and we take the log of that, and then we get the size of the line, which is 13 bits per address. And so the next step is, because we have both of these, the line and the word, and we already know what the total address is, which is 32 bits. And then all we have to do is solve for t here. So line is 13, the word is 5, and so we move it over, so t equals 32 minus 13 minus 5, which is 14. That's the end of this.
Step 4.
we're going to convert this address, our hex address, into binary. So starting from the left side, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Next we have our E, which is 14 in decimal. So we're 1, 1, 1, 0. Next is our 6. So it's 0, 1, 1, 0. And we have another 0. 1, 2, 3, 4 zeros. And our 2. So 0, 0, 1, 0. So from here, we look at our tag, line, and word. So starting from our right side, our first 5 is our word. Then our next 13, starting from here all the way to here, is our line. And the rest on the left side, the 14 is our tag. And combined our tag all the way to our line, that is our block.
Okay, so what we've done now is we've moved our binary address onto the piece of paper here to make the next part easier to illustrate. So this is the binary address, and we've divided it into the tag, the line, the word again, and we have the block. So in order to solve all our questions, actually we just do a lot of binary addition. And to help us do that, I've prepared this handy dandy binary ruler that we can just line up and write down a bunch of numbers. So why don't we start with the word, because that's the easiest. I line it up on the right, and we see there's only a single 2. So that means this address is on word 2. The next thing we'll want to do is the full address, probably. So we'll write down the full address. And after lining it up, we have a 2. We have a 2 to the 9, which is 5 to the 512. We have 2 to the 10, 1, 0, 2, 4. We have 2 to the 13 is a 192. We have 16384. And we have 32768. And if we add those all together to save you this process, it's 58882. So this is the address in decimal, and also the cell number in main memory. Next, let's look at the line. If we go back to our address here, if we only have the line and the word, this is basically the same as addressing the cache. So if we line it up here, and we want to divide the cache by the number, by the size of each line, which is the number of words in each line. And that is the 2 to the 5. And how that looks like dividing is just a bit shift to the right. So if I move the piece of paper 5 spaces to the right, then the way it lines up, we can get our line. So 2 to the power of 4 is 16. There's a 32. There's a 256. 512, 1024. And if I add all of this up, I get 1840. And this is the line number in cache. So next we'll take the tag which is super easy, because if we look at it all the way over here, it's just a bunch of zeros. Next, we will want the block, which is, as we said, this portion here. So as it turns out, the tag is 0, so the block is going to be the same as the line, which was 1840. How to get it in general is you would line it up here as well, and you'd be able to do more calculations over here in the same fashion if the tag were anything other than 0. Finally, we want to know other cells in the block. To do this, we take the address and we subtract the word. So address subtracting the word number gives us the first word. Five, 8, 8, 0. To get the last word, we add the size of one word, which was 2 to the 5, so 32, and minus 1. And we add that to the first word. So 5, 8, 8, 8, 0 plus 31 equals the last word. 5, 8, 9, 1, 1. And that's the answer to every single question.